Right now, the most dangerous object in the known universe is not a black hole. A black hole is a local hazard. Stray within a few dozen light years and its gravity devours you. But the universe is vast. The odds of one wandering into our neighborhood are vanishingly small. The supermassive monster at the galactic center sits 26,000 light-years away. Its gravity is a distant whisper. Magnetars do not need to get close. They do not swallow you. They hurt you from halfway across the Milky Way without moving a single kilometre toward you. On December 27, 2004, at 21:30 Universal Time, one of them did exactly that. The dead star responsible carries the clinical designation SGR 1806-20. It sits in the constellation Sagittarius, toward the crowded heart of the galaxy, approximately 50,000 light-years from Earth, nearly twice the distance to the galactic center. Light from its neighborhood began traveling toward us when woolly mammoths still walked across the frozen plains of North America, and the last Neanderthals were disappearing from Europe. For 50,000 years, that light raced through interstellar vacuum, carrying a message no one expected. At 21:30 UT, the message arrived. Every gamma-ray detector in the inner solar system lit up simultaneously. NASA's SWIFT satellite, designed to catch the fading embers of distant gamma-ray bursts, was instantly blinded. Its detectors pegged at maximum and stayed there. The Resi Solar Observatory, built to watch our own sun's high-energy outbursts, was overwhelmed by a flash that did not come from our star at all. The Russian Konus instrument suffered the same fate. Multiple spacecraft, built by separate nations for entirely different purposes, all recorded the same impossible spike. Dr. Rob Rothschild, lead scientist on the SWIFT team, later described the moment with raw honesty. His first thought, "What the hell is that?" His second was worse. "It can't be that far away." Because if it was that far away, the energy was impossible. The numbers confirmed the distance. SGR 1806-20 was no nearby solar flare. It was no modest outburst from a local star system. It was a dead star 50,000 light-years distant, a collapsed core no wider than a city, roughly 20 kilometers from one side to the other. And it had just released more energy in 0.2 of a second than our Sun will generate in 150,000 years. You can drive across 20 kilometers in 10 minutes on a quiet country road. That is the diameter of the object that struck Earth across a gulf so immense the light from it left before the dawn of agriculture. A single teaspoon of its material weighs 4 billion tons. Its surface gravity is 200 billion times what you are experiencing right now. It is not a black hole. It is something rarer, stranger, and far more dangerous in terms of sheer lethal reach across the interstellar dark. The pulse did not just saturate space-based detectors. It reached Earth's atmosphere and physically changed it. Instruments in Fairbanks, Alaska recorded a sudden darkening of the ionosphere, followed by a swelling and reinflation as the planet's upper atmosphere absorbed the gamma-ray blow. Very low-frequency radio signals blinked out for about 30 seconds. The entire day side of the Earth, the hemisphere facing the source, glowed faintly in visible light, a phenomenon never before observed from any source outside the solar system. "Doctor," Brian Gainsler put it bluntly, "if you had been standing on the surface of the Moon, looking back at Earth, you would have seen the entire day side of the planet light up like a giant flashbulb. The Magnetar was so loud it spoke to the whole Earth at once. Not one person on the ground felt a thing. No windows shattered, no alarms went off in the streets. But the most sensitive instruments humanity had ever built recorded a planetary ringing, the ionosphere vibrating like a struck gong, set into motion by an object 100 billion times smaller in volume than Earth itself. That is what a magnetar is. A dead star, a city-sized cinder of ultra-dense matter, wrapped in a magnetic field so extreme that atoms themselves are stretched into thin needles along its surface. When that magnetic field slips, when the crust fractures under the strain, the stored magnetic energy unleashes a directed beam of gamma radiation that can cross tens of thousands of light years and still carry enough force to ionize an entire planet's atmosphere. No supernova can match this reach. A supernova would need to detonate within about 30 light years to cause a mass extinction. A magnetar's kill zone spans thousands of light years, a volume of space tens of millions of times larger. It does not have to be next door. It just has to be somewhere in the galactic neighborhood. And the beam has to point in our direction when the crust finally cracks. The 2004 event was not a direct hit. It was a warning shot from the far side of the galaxy. Yet even at that distance, it left a measurable scar on our planet. The energy released was equivalent to the complete annihilation of roughly half an Earth mass of matter. Had we been 10 times closer, the gamma-ray flux would have stripped the ozone layer and triggered a mass extinction event. The kind of catastrophe Earth has not seen in 250 million years. A single dead star did this. From 50,000 light years. Black holes trap everything, even light. Their danger is close range. Magnetars broadcast death across the void. They do not need proximity. They need only a clear line of sight and a few thousand years of magnetic stress building in their crusts. And there are dozens we know of, perhaps hundreds more we have not found, hidden in the dusty plain of the Milky Way, quiet for now, waiting. So the question is no longer whether the universe contains objects that can reach across the galaxy and touch us physically. The 2004 event ended that debate. The question is, what exactly is a magnetar, and how does a city-sized corpse store the kind of energy that can ring an entire planet from 2/3 of the way to the galactic core? To understand what a magnetar is, you have to start with how it is made. And that story begins with a star far more massive than our own. Stars between roughly 8 and 20 times the mass of the Sun do not fade gently. When they exhaust the last of their nuclear fuel, they collapse. The core, a sphere of iron no wider than Earth, stops generating energy. In that instant, the pressure that had held it up against its own immense gravity vanishes. The core falls inward at a quarter of the speed of light. The entire structure, the mass of a star, crushes down into a sphere roughly 20 kilometers across in less than a second, the size of a city. You can walk 20 kilometers in an afternoon. You can cycle it in under an hour. And within that compact boundary, a magnetar packs more than an entire star's worth of material. The numbers are precise, and they do not fail to stun. A typical magnetar contains between 1.4 and 2.2 times the mass of the Sun, compressed into that 20-kilometer diameter. If you could somehow carve a single cubic centimeter from its surface and bring it to Earth, that teaspoon-sized sample would weigh approximately 4 billion tons. Not 4,000 tons, not 4 million. 4 billion. That is the weight of a small mountain, crushed into something that fits inside a teaspoon. The density at its core reaches 10 to the power of 17 kilograms per cubic meter. Ordinary matter, the kind that makes up your body and this planet, has densities measured in thousands of kilograms per cubic meter. A magnetar is 100 trillion times more dense. And gravity follows density with the same ruthless scaling. The surface gravity of a magnetar is roughly 200 billion times what you are experiencing right now. On the surface of a magnetar, any material object would be flattened instantly into a thin film of subatomic paste. There is no standing on this thing. The surface does not resemble a solid crust as we understand it. The collapse that formed this object did not just compress matter, it rewrote it. In the core of a living star, high temperatures keep atomic nuclei and free electrons buzzing in a hot plasma. When the core collapses, the pressure becomes so extreme that electrons are forced into protons. Proton meets electron, and the reaction strips away any distinction between them. They become neutrons. The entire mass of the star's core, all the iron, all the silicon, all the heavier elements forged in its final days, is crushed into a single, continuous sea of neutrons held together by gravity alone. Think of what that means. A normal atom is mostly empty space. A nucleus sits at the center, tiny and dense, surrounded by a cloud of electrons that fills the atom's volume. In a magnetar, all that empty space is gone. Every neutron is packed against every other neutron, edge to edge, with no room for anything else. The object is, in essence, a single atomic nucleus the size of Manhattan. It is not made of atoms. It is one atom. The strong nuclear force, which normally binds only the protons and neutrons inside an atomic nucleus, now operates across an entire city-sized sphere. Gravity does the crushing, but it is the strong force that stops the collapse. A resistance born of the fact that neutrons refuse to occupy the same quantum state. That resistance is absolute. If you added more mass, gravity would overcome even the strong force, and the object would collapse further into a black hole. A magnetar sits right at the edge. It is the densest form of matter that can exist without becoming something from which light cannot escape. The surface is not solid in any familiar sense. It may have a rigid crust, a lattice of iron nuclei held in place by crushing gravity and magnetic fields we have not yet discussed. Below that lies a fluid sea of neutrons, a superfluid that flows without friction. At the very center, conditions may be so extreme that neutrons themselves dissolve into a soup of quarks, the fundamental particles that make up protons and neutrons. No laboratory on Earth can create these conditions. The particle colliders and heavy ion accelerators we have built produce densities that last for a billionth of a second, in volumes smaller than an atomic nucleus. A magnetar does it continuously, across an entire star. The object that struck Earth in December 2004 was this: 20 kilometers of compressed star stuff, spinning fast, holding itself together with forces that cannot be reproduced anywhere else in the known universe. This city-sized nucleus, this Manhattan of neutrons, released enough energy in 0.2 of a second to match every photon the sun will emit for 150,000 years. That is the corpse of a massive star. That is the platform upon which a magnetic field of immense intensity will be wound. But before we understand how that field is built and what it does to matter, we must first sit with what this object already is, even without its magnetism. A teaspoon weighs 4 billion tons. The surface gravity would shred any known material into a film of subatomic paste within microseconds. The density is so high that light itself bends into a tight curve as it tries to leave the surface, the gravitational lensing warping the view of any nearby observer into a distorted fisheye mirror. And this object is real. We have seen the flares. We have measured the masses. We have tracked dozens of these dead, spinning cores across the galaxy, each one a compact body of physics gone mad. So the question shifts. If the density alone is this extreme, what happens when you add a magnetic field 1 quadrillion times stronger than Earth's? What happens to those neutrons, those iron nuclei on the surface, when you thread them with magnetic field lines carrying more energy than the matter they pass through? That is the next layer. That is where the magnetar becomes something with no analogy, no comforting comparison, no word that does justice to the violence it can unleash. The number itself sounds like fiction. 10 to the 14th to 10 to the 15th Gauss. A quadrillion times the magnetic field you are sitting in right now. Earth's surface field measures about half a Gauss. just strong enough to nudge a compass needle north. A typical neutron star, already an extremist among stellar remnants, carries a field of roughly 10 to the 12th Gauss, 1 trillion times Earth's. A magnetar multiplies that by another factor of 100 to 1000. The jump is not incremental. It is category-shattering. At these intensities, the magnetic field stops being a background condition and becomes the dominant physical reality. The energy stored in a magnetar's field is not a weak overlay on matter. It exceeds it. In ordinary physics, matter has mass, and mass carries an energy equivalent given by Einstein's equation, E equals mc squared. The rest mass energy locked inside every atom, simply because it exists, is enormous by human standards. But inside a magnetar, the magnetic energy density surpasses even that. The field contains more energy in a given volume than the matter occupying that same volume. The field is in command. The matter is along for the ride, and it buckles under the strain. To see how, you have to look smaller, down to the electron. In a normal atom, electrons orbit the nucleus in three-dimensional clouds described by quantum mechanics. The shapes of those clouds determine everything about chemistry. How atoms bond, how solids form, how light interacts with material. A magnetar wipes that familiar behavior away. The magnetic field lines are so intense that they confine electrons to the lowest Landau levels. Landau levels are quantized orbits that charged particles are forced into by extreme magnetic fields. Think of them as rails the electron cannot leave. In a magnetar's grip, the electron's freedom to move perpendicular to the field line is strangled. It can only spiral tightly along the field direction. The atom is no longer a sphere. It is stretched into a thin cylinder roughly 200 times longer along the field line than across it. The electron cloud that once surrounded the nucleus in all directions is now forced into a narrow needle aligned with the magnetic axis. The nucleus itself, heavier and less responsive, still distorts under the same pressure. The result is matter no chemist could recognize. Polymers of iron arranged end to end, not by chemical bonds, but by magnetic coercion. On a magnetar's surface, where the field strength pushes past 10 to the 15th Gauss, iron atoms do not form a metallic lattice of the type we mine from Earth's crust. They assemble into long, thread-like structures, bound in molecular chains with no parallel in any laboratory. The field manipulates electron density so completely that the very concept of a chemical bond becomes a secondary consideration. The magnetic field is the architect. The crust of a magnetar, then, is not a crust as we understand it. It is a landscape of iron whiskers, aligned like a forest of metallic hairs, each spine no wider than an atom, and stretching perhaps a few hundred times that in length. The forces bundling these needles together are electromagnetic, not gravitational, and they resist shear and compression in ways solid-state physics cannot easily model from first principles. The structure is rigid, but its rigidity comes from a different source than any solid you have ever encountered. The quantum effects go deeper. Electrons in these Landau levels occupy discrete energy states, and the spacing between those states is proportional to the field strength. In a magnetar's field, the energy gaps are so large that they shift the entire electronic structure of every atom. Photons trying to interact with these atoms find the allowed transitions have moved. Absorption and emission lines that astronomers use to read the chemistry of stars are twisted into unfamiliar patterns. Light reflecting off this surface would not look like light reflecting off normal iron. Its spectrum would be a scrambled message, written in a language we are still learning to decode. And the field is not static, it twists. It stores torsional energy in the crust and in the plasma-filled magnetosphere above. Every now and then, the crust cracks under the magnetic stress. When it does, the field reconfigures, reconnecting in loops that release their stored energy into particles accelerated to near light speed. That is the starquake. That is the flare. But the quiet state, the 99% of a magnetar's life spent not flaring, is still a regime where matter is permanently altered by forces it cannot overpower. Even the vacuum bends. Quantum electrodynamics predicts that at field strengths above roughly 4 billion Gauss, virtual electron-positron pairs in the vacuum become polarized, aligning with the field and altering the propagation of light. This birefringence of the vacuum, the splitting of light rays into two polarization states, as a crystal might do, has never been directly observed. A magnetar's surface gets you deep into that territory, making the empty space around it optically active. The void itself bends and slows light. At a safe distance, with instruments keyed to the X-ray and gamma-ray spectrum, the sight would be alien. Not just the stabbing iron needles, not just the gravitational lensing that wraps the surface image around the star, but the glow of a magnetic field tearing itself apart in slow motion, the shimmer of electron-positron plasma flickering into existence and annihilating as the field oscillates, the sudden crack of a cross-fracture sending a seismic wave rippling through the entire star at 1/3 the speed of light. All of this happening on an object you could walk across in an afternoon if you were not instantly flattened into a subatomic film. Chemistry, in the normal sense, is absent. The periodic table, with its orderly arrangements of electron shells and oxidation states, becomes a crude approximation that no longer applies. Iron is not iron in the familiar sense. It is an elongated, field-aligned entity whose bonding behavior is dictated by magnetic confinement, not by the sharing or transfer of electrons. Molecules cannot form in any traditional way, because the electron clouds that would mediate chemical bonds are constrained to a single dimension. The periodic table, one of the great triumphs of human understanding, stops being predictive at these field strengths. On March 5, 1979, at 09:51 Universal Time, a dead star in another galaxy spoke. The voice was gamma radiation, and it crossed 165,000 light-years to reach us. Two Soviet spacecraft, named Venera 11 and Venera 12, were cruising through interplanetary space, bound for Venus. They were not carrying telescopes. They were not designed for astronomy. Their mission was to descend into the Venusian atmosphere and measure its composition. But mounted on each probe was a small gamma-ray spectrometer, a scintillation detector meant to map the metals in Venusian soil from orbit. These instruments were sensitive. No one expected them to intercept a cosmic shout from the Large Magellanic Cloud. The detectors were active as the two spacecraft drifted millions of kilometers apart. Then, without warning, their chart recorders slammed against the end stops. The pen Soviet scientist Dr. Eugene Churazov later recalled went off the top of the page. He thought the instrument had broken. Moments later, the data from the second probe arrived, 10,000 kilometers distant, and it showed the same impossible spike. The timestamps were identical. Two separate machines, isolated in the void, saturated by the same event at precisely the same instant. No malfunction can fake simultaneity. The energy that hit the Venera detectors was gamma radiation, the most penetrating form of light, arriving in a pulse that lasted less than a quarter of a second. It was not a slow brightening, it was a hammer blow. The detectors were designed to count photons one by one in the relatively gentle environment of interplanetary space. This event delivered so many photons so fast that the electronics could not count. The signal overwhelmed the circuitry, pegging the output to maximum and staying there for the duration of the pulse. The actual intensity could only be estimated later from the instrument's recovery time and the known saturation threshold. Even those conservative estimates pointed to a source of staggering power. The burst was localized to the Large Magellanic Cloud, a satellite galaxy of the Milky Way, 165,000 light-years distant. At that range, a typical supernova, outshining a billion suns at its peak, might nudge a gamma detector. But only just. This was something else entirely. The flare, later catalogued as SGR 052566, poured out as much energy in 0.2 of a second as the Sun radiates in approximately 10,000 years. It was the first recorded giant flare from a soft gamma repeater, though that term did not yet exist. Soft gamma repeaters had not been classified. Magnetars had not been theorized. The very concept of a neutron star with a magnetic field a quadrillion times Earth's was absent from the astrophysical lexicon. In 1979, astronomers knew neutron stars existed. The Crab pulsar had been discovered a decade earlier, and they knew neutron stars could have strong magnetic fields. But the numbers involved here were outside every model. A neutron star producing a gamma-ray spike visible across intergalactic distances, saturating detectors on a spacecraft designed for planetary science, simply did not fit. The Soviet team spent weeks ruling out every alternative. A solar flare? The sun was quiet and the direction was wrong. A burst from Venus? The probes had not yet arrived, and Venus does not emit hard gamma rays. A nuclear test in space? No nation had detonated a weapon that powerful, and no debris was detected. A timing electronics error? The cross-check between Venera 11 and Venera 12 eliminated that. The signal was real. The source was outside the solar system. One of the immediate puzzles was the brevity. A supernova lasts weeks to months, with the initial gamma flash spread across seconds or minutes, because shock wave takes time to break through the star's outer layers. A gamma ray burst, already under study in the late 1970s, could be short, but the typical duration was seconds to minutes. This spike, less than a quarter second, was far shorter than even the shortest known gamma-ray bursts of the era. The rise time was nearly instantaneous. The detector went from background count rates to saturation in a matter of milliseconds. And then, just as abruptly, the flare decayed. It left behind a slowly fading trail of softer X-rays, a tail that lasted a few minutes, like the fading vibration of a bell after the clapper has struck. That tail carried its own secrets. Quasi-periodic oscillations, rhythmic wiggles in the X-ray brightness that hinted at the object itself vibrating, a neutron star ringing like struck metal. The frequencies of those oscillations, 8 Hz and higher, pointed to a compact object about 20 kilometers across. The numbers matched a neutron star, but a neutron star had no right to be this violent. The event received only limited attention in the West at first. The Cold War still chilled all scientific cooperation, and communication between the Soviet Union and the United States remained fragmented, often delayed by months. The Venera detection was published in Soviet journals and slowly filtered into the broader astronomical community. When it did, it raised an uncomfortable question. What sort of object could unleash that much gamma radiation in that little time from that far away? No existing catalogue of celestial hazards could accommodate it. Later, when the debris had been sifted and the precursor signals reanalyzed, astronomers realized that SGR 052566 had whispered before its scream. 3 years earlier, in 1976, a series of smaller bursts had been recorded from the same region of the sky. They had been filed as probable gamma-ray bursts of the ordinary variety, unremarkable and unexplained. But the 1979 giant flare connected the dots. This source was a repeater. It did not destroy itself in the outburst. It remained intact, coiled, waiting. That repetition was the key clue. A supernova tears itself apart. A gamma ray burst from a collapsing star is a death, not a single shout from a thing that survives. A repeating source meant a persistent object, and a persistent object that could store and suddenly liberate the energy equivalent of the sun's entire output for millennia had to be tapping an energy reservoir that few astrophysicists had yet imagined. The magnetic field was the answer, but that realization would take 13 years. In the meantime, the terminology floundered. The object was called a soft gamma repeater because the spectra peaked in the softer end of the gamma ray range and because it repeated. The name described the behavior, not the engine. The engine, a magnetar, remained hidden, a phantom whose outline was invisible because no one had yet drawn the theoretical map that connected rapid spin, magnetic field decay, and crust-shattering starquakes. What the Venera probes recorded was not just a data point. It was the sudden violent appearance of an entirely new class of object onto the stage of human awareness. Before March 1979, the most dangerous objects in the universe had been, as far as anyone knew, black holes and supernovae. Local threats, contained within their own neighborhoods, lethal, only if you drifted too close. After March 1979, another possibility opened. An object that could sit in a different galaxy and still hit our detectors hard enough to break them. Dr. Churazov, years later, would describe the moment with a simplicity that still carries the shock. The pen went off the top of the page. They checked the other probe. The timestamps aligned. And then the slow, cold understanding settled in. This was not a glitch. This was not a trick of the electronics. This was something real, something that had traveled 165,000 years across the void to arrive on their chart paper, uninvited and unexplained. The question that hung in the air was not what that object was. No one could answer that yet. The question was simpler, and it would echo through the next 2 decades of high-energy astrophysics. If one of these can do this from outside our galaxy, what happens when one speaks closer to us? The answer to that question took 13 years to crystallize. In 1992, 2 theorists gave the unknown engine a name. Robert Duncan and Christopher Thompson published a dense theoretical paper that proposed magnetic field decay as the power source for the mysterious objects astronomers had been calling soft gamma repeaters and anomalous X-ray pulsars. They called their creations Magnetars. The name was deliberate, a new species of star, built not around fusion or rotation, but around a magnetic field so extreme that its slow death could power the most violent outbursts in the galaxy. Their calculations showed that a magnetic field of 10 to the 14 to 10 to the 15th Gauss, if wound into a newborn neutron star by a fast-spinning dynamo, would contain enough stored energy to produce repeated giant flares over roughly 10,000 years. The field would twist the crust until it snapped. The energy released would be instantaneous, directional, and efficient. The Duncan-Thompson model predicted exactly the kind of screaming, repeating sources the Venera probes had glimpsed in 1979. The paper was met with a mix of fascination and skepticism. Many astronomers doubted that a magnetic field that strong could exist in nature. The numbers were beyond laboratory physics, beyond anything tested in a supernova simulation. But the model made a hard prediction. If magnetars were real, their flares would not be confined to theoretical space. They would reach out and touch the physical environment around Earth. 6 years later, one did. On August 27, 1998, a dead star near the center of the Milky Way convulsed. The source was SGR 1900+14, located some 20,000 light-years away in the constellation Aquila. It had been quiet for years, a faint X-ray glow buried in archival data, unremarkable and unobserved. At 10:22 Universal Time, it fired. The flare was not as powerful as the 1979 giant. It ranked as an intermediate event, something between the ordinary small bursts that soft gamma repeaters emit every few years and the full-throated catastrophes that occur once a century. But the energy output wasn't what made August 27, 1998 a turning point. It was the impact at the receiver. This time, Earth was not merely a distant spectator that recorded a spike on a graph. This time, the planet felt it. The gamma-ray pulse, traveling for 20,000 years across the void, slammed into the upper atmosphere. The electromagnetic radiation stripped electrons from atoms in the ionosphere, the charged layer that sits between 80 and 600 kilometers above the surface. The ionosphere is Earth's interface with space, a constantly shifting plasma that reflects radio waves and absorbs high-energy photons. It is sensitive. A solar flare can shake it. A geomagnetic storm can inflate it like a balloon. But no one had ever seen it respond to a source outside the solar system. On that day, it did. Very low-frequency radio stations, the kind used for submarine communication and navigation, began to glitch. VLF signals bounce between the ionosphere and the ground, and their propagation depends on the precise electron density of the lower ionospheric layers. When the density shifts, the signal strength changes. That night, the signal shifted. The effect was small. A minor wobble in amplitude, a faint distortion in phase. No radio operator would have noticed without sensitive monitoring equipment and careful post-analysis. But the data were unambiguous. The ionospheric electron content had been nudged above background levels by a pulse that originated 20,000 light-years away. A dead star the size of a city had reached across a fifth of the galaxy and physically altered the atmosphere of another world. The scientific community did not immediately broadcast this discovery to the evening news. The ionospheric signatures were subtle, extracted from signal logs days later by researchers who knew what to look for. The initial focus was on the astrophysics of the flare itself, spectra, timing, the peculiar soft tail that decayed over several minutes. But as the data were cross-referenced with terrestrial monitoring stations, the larger implication became undeniable. A magnetar had produced a measurable geophysical effect from interstellar distance. This was something new. A supernova at 20,000 light-years is a bright pinpoint of light in a telescope, a photon stream that excites astronomers but leaves the planet untouched. A black hole accretion flare, even from the galactic center, is a gentle trickle of X-rays by the time it reaches us. But a magnetar flare, with its razor-sharp millisecond rise time and its focused beam of hard gamma rays, carries enough punch to deposit energy directly into the Earth's protective shell. The 1998 event did not threaten life. The ionospheric disruption was mild, equivalent to a modest solar flare or a weak geomagnetic disturbance. No satellites malfunctioned. No power grids tripped. The planet shrugged it off. But the margin was now drawn, and it was not infinitely wide. August 27, 1998 was the first time a human instrument recorded a magnetar flare that was not merely a distant astrophysical curiosity. It was a direct physical interaction between a stellar corpse and the planet we live on. The theoretical danger Duncan and Thomson had described in 1992, a highly directional, blinding pulse of gamma radiation that could ionize planetary atmospheres, was no longer theoretical. It was a measured event. The flare also sharpened an uncomfortable question that had been forming since 1979. The distance to SGR 1900 plus 14 was 20,000 light-years. The 1979 flare came from 165,000 light-years. Both had saturated detectors designed for much weaker signals. Both had deposited energy onto spacecraft in interplanetary space. And now in 1998, a smaller event, not even a full giant flare, had disturbed the ionosphere. What was the scaling law? If a magnetar at 20,000 light-years could jostle the ionosphere with an intermediate flare, what would a giant flare do from the same distance? What about from half that distance? A quarter? The mathematics was straightforward. Gamma radiation intensity falls off as the square of the distance. At 10,000 light-years, the same flare would be 4 times more powerful at Earth. At 5,000, 16 times. At 3,000, over 40 times. The numbers were not reassuring. Yet the 1998 flare was not assessed that year in existential terms. The magnetar field was new, small, and still struggling for acceptance. Only a handful of these objects had been confirmed. Many astronomers continued to regard the Magnetar model as speculative, preferring alternative explanations for soft gamma repeaters involving accretion or bizarre binary systems. The ionospheric data, while physically compelling, were met with caution. Measurements of the upper atmosphere are noisy. Solar activity dominates. Separating a tiny stellar signal from the background took months of careful analysis. But the people who specialized in high-energy transients understood what they were seeing. Dr. Kevin Hurley, who had been hunting gamma-ray bursts for decades, was among the first to connect the ionospheric data to the Magnetar model. He recognized that the 1998 flare was a warning. Not a catastrophe, not an extinction event. A warning, a demonstration that the mechanism worked. The galaxy was now known to contain objects that could touch Earth from tens of thousands of light-years away. The term magnetar, coined only 6 years earlier, had been validated not by one dramatic observation, but by an accumulating pattern. The 1979 spike, the 1992 theory, the 1998 ionospheric tap. The pieces were fitting together. That tap was soft. The next one would not be. On December 27, 2004, at 21:30 Universal Time, a dead star in the constellation Sagittarius decided to speak. Its name was SGR 180620. It sat roughly 50,000 light-years from Earth, on the far side of the galactic center, buried in dust and invisible to the naked eye. For years it had done nothing remarkable. A faint X-ray source, catalogued and mostly ignored. Then, in a fifth of a second, it became the brightest object ever detected outside the solar system. The flare began with a main spike lasting 0.2 of a second. In that interval, the magnetar released 10 to the 46 ergs of energy. That number, spoken aloud, is nearly meaningless. Here is what it means. It is equal to the total energy output of the Sun over 150,000 years, compressed into a single pulse. It is the equivalent of annihilating half an Earth mass of matter and converting it into pure gamma radiation. And it happened not at the surface of a giant star, not in the accretion disk of a black hole, but on a sphere of neutrons 20 kilometers wide. Every gamma-ray detector in the inner solar system registered the hit at the same instant. NASA's Swift satellite, launched only a month earlier and still being calibrated, went blind. Its Burst Alert telescope was designed to detect the afterglows of distant gamma-ray bursts, not a hammer blow of hard photons from inside the Milky Way. The instrument saturated instantly. The counts piled up against the detector's ceiling and stayed there, a flat line that meant the source was brighter than anything the engineering team had ever dared model. The same thing happened to RESI, the Reuven-Ramity High-Energy Solar Spectroscopic Imager. RESI was built to study solar flares. It was supposed to stare at the Sun, not at the galactic center. But its detectors were unshielded in all directions. And when the pulse arrived, it overwhelmed the electronics. The spacecraft recorded a gamma-ray signal that was fully saturated across multiple energy bands, a wall of noise that had no place in a solar observation log. The Russian CONUS instrument, carried aboard the WIND spacecraft stationed 1,000,000 miles from Earth, also saturated. CONUS was a veteran. It had been measuring cosmic gamma-ray bursts for a decade. Its designers had built in wide dynamic ranges, expecting to catch rare, powerful events. But nothing in its specification sheets prepared it for a Magnetar giant flare at 50,000 light-years. The signal pegged the meters and left the team scrambling to understand whether their instrument was still functioning. On the ground, the reaction was immediate, disciplined chaos. Dr. Rob Rothschild, lead scientist for the Swift Gamma-Ray Burst team, got the alert on his pager. His first words were, "What the hell is that?" His second thought, "It can't be that far away." Because if it was that far away, if the source truly stood at 50,000 light-years near the galactic center, then the energy was impossible. The numbers did not fit any known physics of stellar flares. They barely fit the physics of thermonuclear detonation. But triangulation from multiple spacecraft confirmed the distance. The source was not nearby. It was not a local gamma-ray burst in a neighboring galaxy. It was inside the Milky Way, in the crowded, star-choked region beyond the core. And yet it had just screamed louder than any extragalactic burst ever recorded. The physical effect on Earth was immediate and measurable. The gamma rays, traveling for 50,000 years through interstellar vacuum, slammed into the top of the atmosphere at 2130 UT. Over the Pacific and the Americas, the dayside ionosphere absorbed the blow. Electrons were torn from atoms in a cascade that spiked the ionospheric electron content by a factor of 1.5 to 2 standard deviations above the daytime baseline. That is the clinical measure. Here is the reality. The upper atmosphere of our planet swelled and ionized as if a solar flare had struck, but no solar flare had struck. The sun was quiet. Very low-frequency radio waves, the kind that bounce between the ground and the charged layers of the ionosphere, suddenly lost their mirror. VLF propagation paths that had been stable for hours folded. Signals being monitored at receiving stations in Alaska, in Canada, in the northern United States went dark. Not a gradual fade, not a flicker, a 30-second blackout. Then slowly the ionosphere began to recover. At the High-Frequency Active Auroral Research Program facility in Fairbanks, Alaska, a place built to study the ionosphere by probing it with high-power radio beams. The instruments recorded something that made the operators stop in their tracks. The electron density profile, normally a smooth curve that rises and falls with diurnal rhythms, went into spasm. It spiked, then it rang. The ionosphere physically oscillated, its height rising, falling several times over the course of minutes as the excess energy dissipated. Dr. Christopher Reynolds, a radio astronomer analyzing the data, later described it as a kind of planetary ringing. The Earth, struck by a dead star 50,000 light-years distant, had literally vibrated. The optical consequence was even harder to comprehend. Dr. Brian Gainsler, an astronomer at the University of Sydney, later calculated what a hypothetical observer would have seen standing on the surface of the Moon, looking back at Earth at the moment of the flare's arrival. The entire dayside atmosphere, he concluded, would have lit up in visible wavelengths, a faint but detectable glow like a giant flashbulb firing across the hemisphere. The Magnetars' gamma rays cascading down through the atmosphere produced secondary particles and photons that made the upper sky fluoresce. For the first time in recorded history, a source outside the solar system made the Earth's atmosphere physically glow. No human eye saw it. It was 2130 UT, mid-afternoon in the Americas, early morning in East Asia. Satellites recorded it. Ground instruments recorded it. The planet itself recorded it, etched into the electron counts and the VLF propagation logs. But if you had been standing outside, looking up, you would have noticed nothing. The visible glow was too faint, too diffuse, buried under the blue of the sky. The ringing was in the radio bands, below the threshold of your senses. The event was invisible, inaudible, and yet it was the most violent physical interaction between Earth and a stellar object since the formation of the solar system. There was no warning. The Magnetar gave no precursor that night. One instant it was a quiet X-ray source among thousands, catalogued and unthreatening. The next, it released more power than the sun has emitted since the time of the dinosaurs. The beam of radiation swept across the galaxy, and by sheer coincidence, Earth was in its path. Had the beam been aimed a fraction of a degree in any other direction, we would have never known it happened. The photons would have passed harmlessly into the void, and the Magnetar would have remained a footnote in a catalogue. Instead, it hit us dead center. And it was 50,000 light-years away. The 1998 flare from SGR 1900+14 had been a subtle tap, a ripple in the ionosphere that required careful analysis to confirm. This was not a tap. A magnetar's magnetic field is not a static cage, it is a wound spring. The field lines are twisted by the rotation of the star, by the churning of the neutron superfluid beneath the crust, by the same physical forces that drive the sun's magnetic cycle, written larger and more violent than any other environment in the universe. Inside that 20-kilometre sphere, the magnetic field stores potential energy on a scale that has no astronomical analogue. And when that energy releases, when the twisted field lines snap or the crust fractures under magnetic stress, it does not leak out gently. It erupts as a directed beam of gamma rays, collimated by the field geometry itself and fired across the galaxy like a rifle shot. The December 2004 flare illustrates the geometry. Ground-based and space-based detectors measured the pulse arriving from a single point in Sagittarius, consistent with a narrow emission cone rather than an isotropic explosion. If the energy had been broadcast equally in all directions, it would have been impossible to account for the observed brightness without violating basic conservation limits. The beam concentrated the energy into a fraction of the sky, a lighthouse flash instead of a floodlight, and Earth happened to be inside the beam. The total output of that 0.2-second spike was 10 to the 46 ergs. That number, stripped of astronomical scaffolding, means the Magnetar converted the mass equivalent of half an Earth into pure gamma radiation and released it in a single pulse. Not over the lifetime of the star, not across the span of a geological epoch. In 0.2 of a second. Imagine every nuclear weapon ever constructed by humanity, detonated simultaneously, and then multiply that by roughly 1 trillion. The result still falls short. The Magnetar's flare operated in an energy regime that no other stellar event outside a core collapse supernova can approach, and it did so with the directionality of a weapon. That beam traveled for 50,000 years through interstellar medium, across the galactic bar, past the dense star-forming regions of the inner disk, and finally struck the top of Earth's atmosphere. At that distance, 50,000 light-years, it still carried enough punch to strip electrons from atoms in the ionosphere, to swell the dayside upper atmosphere, to silence very low-frequency radio communications for 30 seconds, and to make the sky itself fluoresce in visible light. The photon flux at Earth was roughly 1/10,000th of a watt per square meter. That sounds trivial. It is not. It is the energy of a distant city-sized object making our planet's atmosphere physically glow. Now compare this to a supernova, the traditional benchmark of cosmic threat. A core collapse supernova can outshine an entire galaxy of stars for a few weeks. Its total energy output is roughly 100 times that of the 2004 Magnetar flare, released over months. but that energy is radiated isotropically, and the lethal portion, the hard radiation capable of stripping Earth's ozone layer, drops off with the inverse square of distance. Astronomers calculate that a supernova must occur within about 30 light-years of Earth to cause a mass extinction. Within that radius, the gamma rays and cosmic rays from the blast are intense enough to shatter nitrogen and oxygen molecules in the stratosphere, producing nitrogen oxides that catalyze ozone destruction. The ozone layer thins and surface ultraviolet radiation spikes to levels that kill phytoplankton, collapse food webs, and trigger a cascade of extinctions. 30 light-years is the kill zone for a supernova. That volume, mapped onto the local stellar neighborhood, contains perhaps a few hundred stars. The statistical probability of a supernova detonating inside that radius over the course of 1 billion years is low. The last one that came close may have been the progenitor of the local bubble, a cavity of hot gas around our solar system blown by ancient supernovae several million years ago. But that explosion was more than 300 light-years away, well outside the lethal radius. Now consider the Magnetar. The 2004 flare from 50,000 light-years ionized the atmosphere and set the Earth ringing. It was not lethal, but the energy it delivered to Earth was only a tiny fraction of what a flare 10 times closer would deliver. And a Magnetar does not need to drop its entire energy budget onto the planet. The directed beam is concentrated. The damage to the ozone layer comes not from a diffuse bath of gamma rays lasting weeks, but from a narrow, instantaneous spike that deposits its energy in a single atmospheric layer. The chemistry of ozone destruction is nonlinear. A short, intense pulse can be more destructive than a longer, lower-dose exposure because it overwhelms the atmosphere's repair mechanisms before they can respond. Kevin Hurley, the Magnetar researcher at UC Berkeley, ran the numbers. If the 2004 flare had originated not at 50,000 light-years, but at 5,000 light-years, 10 times closer, it would have stripped the ozone layer. The surface UV flux would have risen to levels unseen since the Great Permian extinction. The food webs of the ocean would have collapsed. Agriculture, if any civilization existed to conduct it, would have been impossible. A single flare from a single dead star, 10 times closer, would have ended the world as we know it. And 5,000 light-years is not a special number. A 2023 study, led by Jonathan Granot, extended the analysis. A giant flare from any magnetar within roughly 30,000 light-years, the team concluded, could cause catastrophic ozone depletion and trigger a mass extinction event. 30,000 light-years. That is the radius of the entire galactic disk. We have confirmed about 30 magnetars in the Milky Way. Population models built from supernova rates and the fraction of neutron stars that become magnetars suggest the true number is in the hundreds. Many are hidden behind the dense dust lanes of the galactic plane, invisible to X-ray surveys. Many are dormant, their magnetic fields wound tight but not yet discharging. A young magnetar discovered in 2020, Swift J ETI 18.016007, is only about 240 years old, measured from its spin-down. It sits roughly 21,000 light-years away. It is already flaring. It was born during the American Revolution, and its magnetic field has been decaying and twisting ever since. It will almost certainly produce a giant flare during the roughly 10,000-year active window of its magnetic decay. When that flare erupts, its beam will sweep across some narrow swath of the galaxy. Whether that swath includes Earth is pure chance. The statistics of beam geometry are not reassuring. A typical emission cone might be a few degrees across. The probability that any given flare is aimed directly at Earth is small, on the order of 1 in 1,000 or less. but with hundreds of magnetars, each capable of multiple giant flares during their active lifetimes, the aggregate probability over a million-year timescale is no longer negligible. It sits somewhere between unlikely and we cannot afford to ignore it. Kevin Hurley ran the calculation. He ran it more than once because the number kept coming back the same and he did not like what it told him. If the December 2004 flare had originated not from 50,000 light-years but from 5,000, 10 times closer, it would have stripped the ozone layer. Not partially, not temporarily, stripped it. The result would have been a mass extinction event on a scale not seen since the Permian die-off 250 million years ago. Surface ultraviolet radiation would have climbed to levels that unravel proteins in phytoplankton, the base of the marine food web. Crops would have failed. The planet's biological scaffolding would have buckled. That is not speculation. That is a calculation rested on the measured energy of the 2004 pulse and the known chemistry of the upper atmosphere. Here is the physics behind the number. When high-energy gamma rays strike the stratosphere, they shatter nitrogen and oxygen molecules into free atoms. Those atoms recombine into nitrogen oxides, NO and NO2, which act as catalysts for ozone destruction. A single NO molecule can destroy thousands of ozone molecules before it is washed out of the atmosphere, cycling through the same reaction again and again. The process is nonlinear. A short, intense pulse of gamma radiation is more destructive than the same total energy spread over weeks, because it floods stratosphere with catalytic molecules faster than natural repair mechanisms can compensate. The ozone layer loses thickness. Ultraviolet radiation at the surface rises. Biology absorbs the consequences. The 2004 flare at 50,000 light-years delivered roughly 1/10,000th of a watt per square meter at the top of Earth's atmosphere. That was enough to ionize the dayside ionosphere, to swell it by several kilometers, to generate a faint, visible glow, and to ring the planet's electromagnetic cavity like a struck bell. It did not deplete the ozone layer, because the gamma flux, though intense, was spread over to a large area and was too brief at that distance to drive the catalytic chemistry past the threshold of significant depletion. It was a physical disturbance, not a biological threat. Move the source 10 times closer. The inverse square law says the flux increases by a factor of 100. Same flare, same 0.2-second pulse, same total energy of 10 to the 46 ergs. But now the beam strikes Earth at 1/100th of a watt per square meter. 100 times the intensity that made the ionosphere glow. At that flux, the catalytic cascade in the stratosphere saturates. The nitrogen oxide production spikes. The ozone column thins by 50% or more over a period of weeks to months. Surface UVB radiation doubles, then triples. The planet's surface becomes hostile to life that evolved under an intact ozone shield. That is the scenario Hurley calculated, 5,000 light-years. Extinction. But Hurley's number was a conservative benchmark. In 2023, Jonathan Granot and his collaborators published a more comprehensive analysis in the Astrophysical Journal. They modeled ozone depletion as a function of flare energy and distance, incorporating updated atmospheric chemistry codes and a wider range of flare parameters. Their conclusion was sobering. A giant flare from any magnetar within roughly 30,000 light-years could cause catastrophic ozone depletion and trigger a mass extinction event. 30,000 light-years. That radius encloses the majority of the Milky Way's disk as seen from Earth. It sweeps through the Sagittarius arm, the Perseus arm, the dense, star-forming regions of the inner galaxy, and vast stretches of the galactic plane, where stars are born and die in their millions. It is a volume containing not dozens of stars, but hundreds of millions. And buried among them, the hidden population of magnetars. The supernova kill zone, remember, is a bubble roughly 30 light-years across, containing perhaps a few hundred low-mass stars and no known imminent supernova candidates. The magnetar kill zone is a disk 60,000 light-years wide, containing much of the visible galaxy. The difference is not a matter of degree, it is a difference in kind. Now consider what happens if the flare originates even closer. The nearest confirmed magnetar candidate is 1e 2259 plus 586, at a distance of approximately 8,000 light-years. It is not a hypothetical object. It is a catalogued source, an anomalous X-ray pulsar that has shown outburst activity in the past. It sits inside what Granot's study defined as the danger envelope. If 1e 2259 plus 586 were to produce a giant flare comparable to the 2004 event, the gamma flux at Earth would be roughly 40 times more intense than the pulse that rang the ionosphere in 2004. 40 times the swelling, 40 times the electron stripping, 40 times the catalytic assault on the ozone column. The result would not be a subtle atmospheric perturbation. It would be a full-blown ozone crisis. The recovery timescale for the ozone layer after an event of that magnitude is measured in decades, not months. During those decades, surface UV radiation would remain elevated. Phytoplankton populations would crash. Marine ecosystems that depend on them would follow. Terrestrial plant life would suffer DNA damage at the cellular level, reducing crop yields and stressing forests already weakened by climate disruption. The cascade would touch every trophic level on the planet, and 1e 2259 plus 586 is the nearest magnetar we know about. The key word is no. The census of galactic magnetars remains a fraction of what population models predict. We have confirmed approximately 30. The models suggest hundreds. Some of those hidden objects almost certainly lie closer than 8,000 light-years. Their X-ray glow buried behind the thick dust lanes of the galactic plane, their magnetic fields wound tight and silent, their presence entirely unsuspected. They are not hypothetical. They are merely uncounted. The 2004 flare from SGR 1806-20 was a warning shot. It came from the direction of the galactic center, a region dense with stars and stellar remnants, a region where magnetars are expected to cluster. It was not an extinction event because distance diluted the beam. 50,000 light-years of interstellar space absorbed none of the gamma rays. Gamma photons stream through the interstellar medium almost unimpeded. But it spread the beam over an enormous area, reducing the flux at Earth to a level that was measurable but not lethal. That margin, the gap between what the 2004 flare did and what it would have done at 5,000 light-years, is precisely a factor of 10 in distance. A factor of 10 is not a wide safety margin on galactic scales. The galaxy is 100,000 light-years across. The difference between 50,000 and 5,000 is a rounding error in the geometry of the Milky Way's spiral arms. A factor of 10. If the magnetar that produced the 2004 flare had been born in a different star-forming region, if its progenitor star had been drifting slightly closer during the millions of years before it collapsed, if the random walk of stellar orbits had placed it 10 times nearer to the Sun, we would not be here to analyze the event. The flare would have come and gone in 0.2 seconds, and the ozone layer would have been torn open, and the biosphere would have entered a new extinction interval, and no one would have known what hit them. That is the razor's edge on which the history of life on Earth has always balanced. Not against the steady grind of geological forces which operate on timescales long enough for evolution to respond, but against a class of object that can deliver extinction in a fraction of a second from a distance so vast that light itself requires 100 human lifetimes to cross it. The 2004 flare did not kill us because of distance. Simple, indifferent distance. The same distance that gave the photons 50,000 years to travel, spreading outward in their narrow cone until they were just dilute enough, just weak enough, to be survivable. The dead star in Sagittarius had no intention. It had no aim. It simply discharged its wound spring, and the beam swept past our position, and we happened to be far enough away. Next time we may not be. We have confirmed 30 magnetars in the entire Milky Way galaxy. That is the number in the catalogues, the number astronomers can point to and say with certainty, this object, at these coordinates, is a magnetar. 30 is not the real number. No scientist in the field believes 30 is the real number. The population models tell a different story. They start with the known supernova rate in the Milky Way, Hurley 2 per century, and the fraction of massive stars that produce neutron stars rather than black holes. They factor in the estimated proportion of neutron stars born with magnetar strength fields, which hovers somewhere around 10%. They integrate over the 10,000-year window, during which a magnetar's magnetic field remains active enough to produce giant flares. The arithmetic does not produce 30, it produces hundreds. Some models push the output past 1,000. The Milky Way should be threaded with magnetars like veins through rock. Yet we see 30. Where are the rest? The first answer is dust. The Milky Way is a flat disk of stars and gas 100,000 light-years across, and Earth sits embedded inside that disk roughly 26,000 light-years from the center. When we look along the plane of the galaxy, we look through dense lanes of interstellar dust that absorb visible and low-energy X-ray light with brutal efficiency. A magnetar on the far side of the galactic center, 50,000 light-years beyond the core, is invisible to us not because it is dim, but because it is buried behind a wall of obscuring matter thicker than any telescope can penetrate. The same dust lanes that hide the far side of the galaxy hide the magnetar population that almost certainly lives there. The second answer is time. Magnetars do not flare continuously. They can sleep for decades, centuries, longer than we have had instruments sensitive enough to detect them. A dormant magnetar emits a steady X-ray glow from its hot surface, but that glow is faint, easily lost among the thousands of other X-ray sources crowding the galactic plane. It takes a flare, a sudden violent spike in luminosity, to pull a magnetar out of the noise and announce its existence. If a magnetar has not flared since the era of X-ray astronomy began in the 1960s, we have no way to know it is there. It is waiting. Silent, invisible, wound. The third answer is the most unsettling. We are still finding them, and every new discovery reveals how many we must be missing. In 2020, an automated sky survey flagged a new X-ray source in the constellation Sagittarius. Astronomers pointed the SWIFT satellite at the coordinates and found a young neutron star spinning once every 1.36 seconds. Its X-ray spectrum hard and hot, its spin-down rate indicating a surface magnetic field of roughly 2 × 10⁻14 Gauss. They named it Swift J8820.0 to 1607. It sits approximately 21,000 light-years away, and it is young, only about 240 years old, measured from the rate at which its rotation is decelerating. Its light, the light we see now, began crossing the galaxy when the American Revolution was still a living memory. The object itself is younger than the United States, a 240-year-old magnetar, active, flaring, inside our own galaxy, and we had no idea it existed until 2020. Swift J8820.02607 is not an outlier. It is evidence of how incomplete the catalogue remains. If a magnetar this young and this bright could evade detection until the third decade of the 21st century, How many older, colder, dimmer magnetars are still anonymous? How many are older than human civilization? Their surfaces cooled to temperatures that render them almost indistinguishable from ordinary neutron stars. Their magnetic fields wound tight and waiting. A discovery in 2022 deepened the discomfort. Astronomers identified a magnetar with an extraordinarily long rotation period of 6.67 hours. 6 2/3 hours to complete a single spin. That is nearly 24,000 seconds, an eternity in neutron star terms. A magnetar that's slow should not be able to power the X-ray emission we see from it. Standard magnetar theory says the magnetic field decays too rapidly in slow rotators. The currents in the magnetosphere falter. The engine stalls. Yet this object shines. It pulses. It demands an update to the models. And if the models need updating for the magnetars we can see, what does that say about the ones we cannot? Krissa Kuveliutu has spent a career cataloguing these objects. She was there in the 1990s when the magnetar hypothesis was still a contested theory, when soft gamma repeaters and anomalous X-ray pulsars were two separate puzzles no one had yet connected. She watched the evidence accumulate, watched the category fill with confirmed members, watched the population estimates climb. Her assessment carries the weight of that history. We keep finding them. Every time we find a new one, we realize how many more there must be. The galaxy is full of traps, full of traps. That is not poetic language. That is a quantitative statement about an incomplete sample. There is no monitoring system. No satellite dedicated to scanning the galaxy for magnetar flares. No early warning network that can alert the world that a pulse of gamma radiation is inbound. The 2004 flare was detected because multiple spacecraft happened to be pointing in the right direction when the spike arrived. And even then, the detectors saturated instantly, their electronics overwhelmed before they could measure the peak of the pulse. If a flare arrives tomorrow from a magnetar we have never catalogued, and there are certainly many, the first notice we receive will be the flare itself. There will be no warning. There will be no time to prepare. The next flare could come from any direction. The galactic center is a natural candidate, dense with stars and stellar remnants, but magnetars are not confined to the core. They form wherever massive stars are born and die. The spiral arms, the star-forming regions scattered through the disk, the random orbits of dead stars that have drifted for millions of years since their violent birth. A magnetar could be sitting 30,000 light-years away in the Perseus arm, invisible behind a dust cloud, its field wound to the breaking point, its crust stressed to failure, and we would not know it until the light reached us. The galaxy is not a map, it is a fog, and we are peering into that fog with a census of 30 when the real number is closer to 300 or 500 or 1,000. What is hiding in the gaps? The magnetar has already spoken, but what made it speak? That question, the trigger mechanism, remains unsettled. After the flash, after the ionospheric ringing, after the ozone layer calculations, we still do not know what exactly lights the fuse. Two models compete for the answer. Both are grounded in physics that cannot be tested in any laboratory. Both fit some of the data and fail to predict the rest. The first model is a starquake. A magnetar's crust is not like planetary rock. It is a rigid lattice of iron nuclei pressed into a crystal by gravity 200 billion times Earth's. The magnetic field threads through this crust, its field lines anchored in the solid lattice. As the field decays over thousands of years, it exerts a twisting, wrenching stress on the crust. Stresses the crystal cannot relieve slowly. The strain builds, the crust holds, then it does not. With a sudden catastrophic fracture, the crust shifts, cracks propagate at near-light speeds through the lattice, and the magnetic field tied to that crust violently reconfigures. The seismic energy released in that rupture. An earthquake on an object 20 kilometers wide, with a density 100 trillion times water, heats the surface, drives currents, and unleashes the pulse of gamma rays that crosses the galaxy. The second model is magnetic reconnection. Here, the energy does not come from the crust at all. It is stored in the magnetosphere, the region of space around the magnetar, where the magnetic field lines dominate completely. In the Quadrillion gas regime, those field lines can twist and shear, building up magnetic tension until they snap. Literally snap. The field lines break and reconnect in a new configuration, releasing the stored magnetic energy in a burst of radiation and particle acceleration. The mechanism is analogous to a solar flare, but the scale is almost impossible to map. The field strength, the energy density, the speed of the process. On the Sun, reconnection can release the equivalent of millions of hydrogen bombs. On a magnetar, the same process, if that is what it is, releases the equivalent of the Sun's total output for 150,000 years. Which model is correct? The evidence is maddeningly ambiguous. The decaying tails of giant flares exhibit quasi-periodic oscillations, intensity ripples at specific frequencies that modulate the gamma-ray afterglow. Those frequencies fall in the range expected for seismic vibrations of the neutron star crust, ringing of the entire star like a struck bell, but at thousands of hertz. That fits the starquake picture. The crust fractures, excites normal modes, and the vibrations modulate the X-ray signal until the crust quiets. Yet the same frequencies also match the expected behavior of magnetospheric oscillations. Standing waves trapped in the magnetic bubble, vibrating at a different set of eigenmodes. Two different physical systems, two different locations, producing signals that cannot be distinguished with current instruments. So the quasi-periodic oscillations, the clearest clue, are not a smoking gun. They are a mirror reflecting whichever model you already prefer. Theoretical modeling does not break the tie. Starquake simulations can produce flares of the observed energy, but only if the crust is unrealistically strong, or the field is stronger than measured. Magnetospheric reconnection simulations can produce flares of the observed energy, but only if the magnetosphere is loaded with far more magnetic energy than models predict can accumulate before an instability sets in. Both require something extra. Both leave a gap between what the equations say should happen and what the detectors recorded. And that is just the trigger. The origin of the magnetic field itself is an even deeper unknown. How does a neutron star wake up carrying a quadrillion gas field that should, by all rights, tear it apart? Again, two models. Again, no resolution. The fossil field hypothesis says the field is inherited from the progenitor star's core. Massive stars already possess strong magnetic fields, hundreds to thousands of Gauss in their interiors. During core collapse, the field lines are dragged inward with the infalling matter, compressed and amplified by flux conservation. Squeeze a field threading a stellar core down to 20 kilometers, the math says, and you approach Magnetar strengths. The problem: that amplification assumes a perfectly ordered collapse, a neat spherical squeezing. Real supernovae are messy, turbulent, asymmetric. The field gets tangled, cancelling itself before it can amplify. For the fossil model to work, the progenitor must rotate just fast enough to keep the field ordered, but not so fast that it disrupts the collapse, a narrow and implausible window that many stars may never hit. The dynamo model sidesteps that requirement. It says the field is not inherited at all. It is born in the first few seconds of the neutron star's life. If the newborn neutron star is spinning with a period of only a millisecond or two, a rotation rate that makes a kitchen blender look stationary, then the convective motion of the dense, hot, ionized fluid inside the star, can act as a dynamo, generating and amplifying a magnetic field from a weak seed. The math of convective dynamos, adapted from the Sun and Earth, suggests that a fully convective proto-neutron star spinning that fast can spin up fields to 10 to the 15th Gauss before it cools and the dynamo shuts off. The problem: you need that millisecond birth spin. Supernova simulations that try to track angular momentum from core collapse routinely fail to produce neutron stars spinning that fast. The spin gets shed in the explosion, lost to the ejector, carried away by gravitational waves. Most simulated neutron stars are born spinning 10 or even 100 times slower than the dynamo model demands. A 2021 study offered a potential crack in that wall. The simulations that best reproduced the explosions known to have birthed observed magnetars tended to be asymmetric: jets, kicks, clumpy ejector. Those asymmetries can preserve angular momentum in the core, funneling it into the proto-neutron star instead of letting it escape. The explosions that make magnetars may be the violent, lopsided ones, the ones that blast the remnant across the galaxy at hundreds of kilometers per second, while also giving it the spin it needs. Intriguing but not proof. No consensus exists. The sample of well-modeled magnetar-forming supernovae is too small. The physics of core collapse too stubbornly complex. What is not ambiguous is the clock. Whether the field is fossil or freshly minted, it decays. Magnetic energy leaks away through currents, through reconnection events, through cracking and heating the crust. The brightest, most violent phase of a magnetar's life lasts about 10,000 years, a blink in cosmic time. After that, the field drops below the threshold for giant flares, and the magnetar fades into the background of ordinary neutron stars, its danger spent. That 10,000-year window is the period of threat. It is also the only window we have to detect these objects before they go quiet. And within that window, the flares remain unpredictable. No precursor signal reliably announces an imminent giant flare. No steady X-ray brightening. No change in spin-down rate. No spectral shift has ever been shown to precede the hammer strike. The starquake may build stress slowly over months or years before the crust gives, or it may trigger catastrophically in a single instant. The magnetosphere may accumulate energy like a capacitor charging, then discharge without warning. We do not know because we have never caught a magnetar in the act of preparing to fire. We only see the aftermath, the saturated detectors, the ringing ionosphere, the sudden, inarguable evidence that something somewhere just broke. And that ignorance is not abstract. The flares that saturate the detectors, the flares that can cross 50,000 light years and still shake the atmosphere. Those flares are powered by a mechanism we cannot describe, in a magnetic field we cannot explain, on a dead star we cannot predict. The next one could be building right now. The crust of some anonymous magnetar buried in the galactic plane, stress accumulating along a fault line in a crystal lattice 1 trillion times denser than granite. The field twisting in the magnetosphere above it like a rubber band stretched over a city-sized sphere. We will see the flare when it arrives. We will scramble to triangulate its origin. We will measure its energy, model its spectrum, catalogue its aftermath. But we will not have seen it coming. What is the mechanism that no telescope can observe? And if we cannot predict it, can we ever be ready? The magnetar is a dead star, but it is also a laboratory. A laboratory that operates at densities beyond nuclear saturation, magnetic field strengths that alter the vacuum itself, and temperatures that probe the very composition of matter at its deepest limit. No experiment on Earth can reproduce these conditions. No collider can compress matter this far. And yet here it sits, 20 kilometers across, radiating its secrets in thermal X-rays that cross the galaxy. The question of what lies inside a magnetar is not a detail. It is the single most important unsolved problem in the physics of dense matter. Begin with the density. A magnetar compresses 1.4 to 2.2 solar masses into a sphere the size of a city. The average density exceeds 10 to the power of 17 kilograms per cubic meter. To put that number somewhere, you can feel it. A sugar cube of magnetar material, placed on a terrestrial scale, would register 4 billion tons. But the average density is not the interesting part. The interesting part is what that density does to the nuclei themselves. At the surface, the matter is a rigid lattice of iron nuclei, the crust that may or may not fracture in a starquake. Descend a few hundred meters, and the pressure rises. The iron lattice is still there, but the nuclei begin to deform. Go deeper, a kilometre or so into the crust, and the pressure reaches several 100 billion times Earth's atmosphere. The nuclei can no longer hold their electrons. The electrons are stripped away, forming a degenerate gas that permeates the lattice. Go deeper still, and the electron gas itself becomes relativistic, its pressure dominating the structure. Then the density crosses a threshold, at roughly 400 million tons per cubic centimetre. Nuclear saturation density. The individual nuclei lose their identity. The iron dissolves. Protons and electrons are crushed together, forced into neutrons by the inverse beta decay that powers the whole collapse. For the bulk of the star, the matter is now a fluid of neutrons, with a small admixture of protons and electrons, all degenerate, all compressed beyond anything a nucleus knows on Earth. This is the core of a neutron star. This is where the magnetar's secret lies, because the density does not stop at nuclear saturation. In the inner core, the central few kilometers of the star, the density climbs to 5, maybe 10 times nuclear saturation. And here, at these pressures, the neutrons themselves begin to lose their identity. The individual hadrons, the neutrons and any surviving protons, may dissolve. The quarks that make them up, normally confined inside the hadrons by the strong force, may become deconfined. A quark-gluon plasma, the material of the universe's first microseconds, may sit in the heart of a 20-kilometre dead star, bottled by gravity and wrapped in a quadrillion Gauss field. This is not speculation. It is a prediction made by quantum chromodynamics, the theory of the strong force. But it is a prediction that cannot be tested in any collider. The Large Hadron Collider can produce quark-gluon plasma in tiny, hot fireballs that expand and cool in a fraction of a second. A magnetar keeps it confined. A magnetar holds it at near zero temperature, packed to densities that no accelerator can approach. If the core is quark matter, it is a form of matter that has not existed freely since the universe was a few seconds old. And quark matter may not be the strangest thing at the core. At these densities, the Pauli exclusion principle fills all the lowest energy states for neutrons. The system can lower its energy by converting some of those neutrons into hyperons, baryons that contain a strange quark instead of just up and down quarks. A lambda particle here, a sigma particle there. The appearance of hyperons softens the equation of state, makes the matter more compressible. A star with a hyperon core is a different object than one made purely of neutrons. It cools differently, it vibrates differently, and it may not be stable at all. Too many hyperons, and the equation of state collapses, the star buckling into a black hole that the magnetic field cannot prevent. Then there is the possibility of strange matter. The hypothesis that a mix of up, down, and strange quarks is the true ground state of nuclear matter. If that is true, and if a magnetar core can seed the conversion, then the entire star could transition to a strange quark star, a single gigantic hadron held together by gravity and the strong force with no neutrons at all. None of this is settled. The equation of state of matter at supernuclear densities is the central unsolved problem of neutron star physics. It is the mathematical relationship between pressure and density in the regime where nuclear forces transition from repulsive to attractive to unknown. The equation determines the star's maximum mass, its radius for a given mass, its cooling rate, its oscillation frequencies. It determines whether a core is neutrons, quarks, hyperons, or something unnamed. And it cannot be measured in a laboratory. It can only be inferred from neutron stars. Magnetars make the measurement possible. A neutron star's surface temperature and its cooling history are direct probes of its interior composition. Magnetars emit thermal X-rays, soft X-rays from their hot surfaces, temperatures of a few million Kelvin, that carry information about what is happening deep inside them. If the core contains hyperons, the star loses energy faster through neutrino emission, cooling more rapidly than a star made of neutrons alone. If the core contains a quark-gluon plasma, the neutrino emission signature changes again. Young magnetars like Swift J8810-1607, found in 2020 and only about 240 years old, offer a fresh, hot window into the interior, their thermal glow still reflecting the heat of formation. Measure that surface temperature precisely over years, track how it drops, and you measure the physics of matter at 10 times nuclear density. The magnetism adds another layer of diagnostics. At magnetic field strengths of 10 to the 15th Gauss, quantum electrodynamics enters a new regime. The vacuum itself becomes birefringent. Light traveling through the magnetosphere is split into two polarization modes, which scatter differently off the charged particles trapped along the field lines. This effect, predicted by QED and measurable in the pulsed X-ray emission from magnetars, allows astronomers to probe the magnetic field geometry in ways that standard neutron stars cannot provide. The vacuum is not empty around a magnetar. It behaves like a medium. It bends, slows, and polarizes radiation in ways that test our most fundamental theory of light and matter. Photon splitting. A single high-energy photon decaying into two lower-energy ones becomes possible above 10 to the 13th Gauss. Impossible in any laboratory, it leaves a signature in magnetar X-ray bursts. Telescopes like NICER and NuSTAR actively search for it. Every burst, every pulse, every slight change in the X-ray spectrum of a magnetar is a data point from a laboratory that cannot be built on Earth. But that laboratory is locked. The crust hides the core. The magnetosphere scatters the photons. What reaches our telescopes is a heavily processed signal, filtered through layers of extreme physics, each of which introduces its own uncertainties. Inferring the equation of state from the thermal X-ray cooling curve requires modeling the crust composition, the magnetic field structure, the neutrino emissivity, and the surface temperature distribution, all of which are themselves uncertain. It is astrophysical inference at its most indirect, the hardest measurement in physics, and yet it is the only measurement. There is no alternative experiment. No particle collider on Earth will ever reach the energy densities of a magnetar core. Laser-driven compression of pellets can briefly approximate the temperatures, but not the pressures, not the sustained equilibrium. The dense matter in these stars, the strange quarks, the hyperons, the broken vacuum, all of it is forever beyond direct touch. When the crust fractures and a giant flare erupts, we get a violent, blinding glimpse of the energy stored in the field. But the star remains sealed. The flare tells us about the magnetosphere and the crust, the quiet thermal glow, the years-long cooling, the subtle modulations in the pulsed X-ray light. Those are the only signals that carry a whisper from the core. Fast radio bursts are one of the deepest puzzles in modern astronomy. They arrive without warning. A spike of radio energy, sometimes lasting less than a millisecond, appearing from random points in the sky, then vanishing. The first was found in 2007, buried in archival data. Since then, telescopes have detected hundreds more. They come from every direction. They are generated by events so powerful that they outshine entire galaxies, briefly, in radiolight before winking out forever. And until April 2020, no one had ever seen one come from inside the Milky Way. The event that changed everything began on April 28, 2020. A magnetar named SGR 1935-2154, a known object in the constellation Vulpecula, erupted. It had been active for weeks, firing off smaller X-ray bursts, building towards something larger. Then, at 14:34 Universal Time, it produced a spike lasting roughly 6 milliseconds. Two instruments detected it simultaneously. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, a radio telescope in British Columbia, designed to survey the sky for precisely this kind of transient signal, and STARE-2, a small array of 3 radio dishes in the southwestern United States, built by a graduate student specifically to catch nearby FRBs. Both saw the same thing, a bright, fast, highly polarized radio burst, originating from a point on the sky that aligned exactly with the known position of SGR 1935+2154. The Magnetar had become the first object ever caught in the act of producing a fast radio burst. The implications hit like a seismic shock. For 13 years, the origin of FRBs had been debated without a single confirmed source. The energies required were so enormous that only the most violent astrophysical engines could be candidates. Merging neutron stars, collapsing black holes, the evaporation of primordial miniature black holes, or exotic physics involving cosmic strings. Magnetars were high on the list of suspects. Their magnetic fields were the right magnitude. Their flares were violent enough, but no one had observed the connection. Now a Milky Way magnetar had delivered the proof. The burst from SGR 1935+2154 carried a total energy of roughly 10 to the power of 35 ergs in radio waves. That is roughly equivalent to a few thousand times the sun's total output for a millisecond. From a star only 20 kilometers across, that number is staggering. But it came with a complication. While it was easily bright enough to confirm that magnetars can produce FRBs, it was still about 1,000 times less energetic than the typical extragalactic FRBs that had been catalogued for over a decade. The bursts arriving from other galaxies, billions of light years away, were orders of magnitude more powerful. If SGR 1935+2154 had been sitting in a galaxy at a distance of 1 billion light-years, CHIME would not have heard it. This energy gap opened a critical question. Do all FRBs come from magnetars, with the 2020 event merely a low-energy cousin of a broader population? Or did this Milky Way event represent a distinct subclass, while the colossal extragalactic FRBs are generated by something else entirely? The alternative models persist because the evidence is not yet one-sided. A double neutron star merger would release a titanic gravitational and electromagnetic pulse. Computer simulations show that the final moments before such a merger could generate coherent radio emission from the violent interaction of magnetospheres, producing an FRB coincident with a gravitational wave chirp. Mergers of neutron stars with black holes offer similar, even more energetic possibilities. And exotic, compact objects, hypothetical quark stars, strange stars, even primordial black holes, slowly evaporating in a final flash, all remain viable until a second source is identified. What the 2020 observation did was break the deadlock. It proved that magnetars are in the FRB business. The same magnetic field that stretches atoms into needles, that stores the energy of a half-Earth mass annihilation, that then snaps and cracks across the light years. That field can also produce a radio scream bright enough to be heard clear across the galaxy. The mechanism is thought to be a giant flare or a star-starquake that launches a relativistic blast wave into the magnetosphere, compressing the surrounding plasma and generating coherent radio emission through a process called synchrotron maser amplification. As the shock passes through the magnetized electrons, it organizes their emission into a single, ultra-brief radio pulse. But a mechanism is not a census. The search for more Milky Way FRBs intensified immediately. Astronomers trained every available radio dish on every other known magnetar, waiting. Since 2020, none of the other roughly 30 confirmed magnetars have repeated the feat in such spectacular fashion. Several other magnetars have emitted radio pulses, but nothing with the energy and fast transient character of a true FRB. The silence is telling. It suggests that FRB-capable flares are rare, or that they require a specific set of conditions, perhaps a very young magnetar, or one with an unusually twisted magnetosphere, or a particular alignment of the magnetic axis relative to Earth. The search continued in the extragalactic population as well. Some FRBs repeat. The first repeater, FRB 1211102, was localized in 2017 to a dwarf galaxy 3 billion light-years away. Subsequent observations confirmed that it sits within a compact, persistent radio source embedded in a region of star formation. The environment is consistent with a young magnetar, perhaps only decades or centuries old, born in a recent supernova and still enshrouded in its nascent nebula. Other repeaters have been localized to similar star-forming regions. The circumstantial case points to magnetars as the engines of many, perhaps most, repeating FRBs. Non-repeating FRBs, the majority of the population, remain more elusive. Some may be from cataclysmic events, perhaps a magnetar's final collapse into a black hole, a one-time release of energy that would then be silent forever. Others may be from neutron star mergers, as originally proposed. The field is moving fast. Every year, new telescopes like the Deep Synoptic Array and the Next Generation Very Large Array narrow the localizations, reducing the error boxes from arc minutes to arc seconds, pinning individual bursts onto individual host galaxies. With enough numbers, the statistics will settle the debate. For now, the honest answer is that magnetars are confirmed as one FRB engine. Whether they are the only engine or the dominant engine remains unresolved. What is not unresolved is what this does to the profile of a magnetar. The same dead star that can ionize a planet's atmosphere from halfway across the galaxy also hurls millisecond-long radio spikes across the universe with a luminosity that rivals 1,000 suns. It speaks in gamma rays that burn detectors. It speaks in X-rays that probe the crush of quarks and hyperons at its core. And now we know it speaks in radio bands too, with a voice bright enough to outshine an entire galaxy for a heartbeat. This is not a simple object. It is a multi-wavelength weapon, a generator of coherent and incoherent emission across the electromagnetic spectrum, powered by the same twisted magnetic field that can crack its own crust. The FRB connection adds a new dimension of unpredictability. A magnetar might sit silent for decades, its field winding tighter, its crust accumulating stress. When the break comes, it might produce a giant flare, or a fast radio burst, or both, or neither. The burst from SGR 1935 plus 2154 was accompanied by a modest X-ray flare, but nothing on the scale of the December 2004 monster. Yet its radio shout was the first of its kind ever observed. This suggests that the catalogue of magnetar outbursts is incomplete, that there are outburst modes we have not yet sampled. Every new telescope that joins the hunt increases the chance of catching the next one. The CHIME collaboration now produces daily alerts for candidate FRBs, some of them localized to individual galaxies in real time. The Square Kilometre Array, under construction in Australia and South Africa, will be orders of magnitude more sensitive, capable of detecting an SGR 1935 plus 2T154-like event from the nearest dozen galaxies. The next Milky Way magnetar to flare will not catch us by surprise. We will have eyes on it in X-rays, in gamma rays, and in radio. The data will be unprecedented. And then the real question will sharpen. Not whether magnetars can produce fast radio bursts, but what fraction of the unknown magnetar population is capable of doing so. How many silent killers are scattered through the disk of our galaxy, slowly winding their magnetic fields, preparing not only a gamma-ray blast that could scorch our atmosphere, but a radio pulse that could, if aimed our way, overload every unprotected receiver on Earth in a fraction of a millisecond. No one has ever estimated that effect. No study has modeled the impact of a close magnetar FRB on planetary infrastructure. No warning exists, no alarm sounds, no satellite in orbit, no telescope on the ground, no detector array in any nation is designed to alert us that a magnetar is about to flare. The first notice we receive is the event itself, a magnetar giant flare, like the one that struck Earth on December 27, 2004, arrives as a wall of gamma rays traveling at the speed of light. There is no precursor signal that outruns the primary pulse. You cannot evacuate a planet. You cannot shield 7 billion people. You cannot reroute satellites or harden power grids after the photons are already here. The impact and the notification are the same physical event. The electromagnetic pulse from a magnetar flare does not need to be focused into a perfect beam aimed directly at Earth to cause damage. The 2004 event was not aimed at us. We were merely in the path of an expanding shell of energy, a side lobe of a much larger release. And it still ionized our atmosphere, still rang our planet's electromagnetic cavity, still proved that distance was the only barrier between us and extinction. Consider what that means. A magnetar 10 times closer would not be just 10 times more powerful. Distance cuts both ways. Closer is not a linear change, it is a jump. 50,000 light-years spreads the beam over an area 100 times larger than 5,000 light-years. The flux intensity does not just increase, it dominates. The geometry becomes precise. The beaming becomes focused. The result is no longer a brush with a passing shell. It is a direct hit from an object you never saw coming, delivering in a fraction of a second the energy that would take our planet's entire electrical grid microseconds to absorb. What happens when that energy hits? The 2004 flare demonstrated the lower bound. A photon flux of 1/10,000th of a watt per square meter ionized the ionosphere, silenced radio communications, and made the dayside sky glow. Scale that up by a factor of 100 and you get an ozone crisis. Scale it up by a factor of 1,000 and you get the death of photosynthesis on a global scale. Scale it up by a factor of 10,000 and you need new categories for what happens. The numbers change. The physics changes. The outcome is no longer measured in atmospheric disruption. It is measured in the collapse of food webs and the end of agricultural civilization. The Great Quebec Blackout of March 1989 gave a preview of how vulnerable we are to electromagnetic disruption. A coronal mass ejection, a burst of charged particles from the sun, hit the magnetosphere. The impact did not fray our ozone layer or boil the atmosphere. The sun's particles were not energetic enough, but they were energetic enough to disrupt the power grid in Quebec. 85,000 people lost electricity in the middle of a cold night. Hospitals switched to emergency generators. Traffic signals went dark. The blackout lasted 9 hours and cost hundreds of millions in economic losses. A magnetar at a few thousand light-years does not generate a gentle breeze. It generates the electromagnetic equivalent of a sledgehammer blow. Satellites are more vulnerable than ground infrastructure. They sit above the atmosphere with no shielding except their own thin aluminum skins. The global communications network does not exist without these satellites. We rely on them for everything: financial transactions, weather forecasting, navigation, emergency response, military coordination. Replacement satellites are not waiting in warehouses. The manufacturing capacity for replacement systems would take years to ramp up. Now consider what we have built to watch for this threat. Nothing. Jonathan Granot, the astrophysicist whose team modeled the extinction-level ozone depletion scenario, put it without embellishment. We know black holes are dangerous if you get too close, but they are local hazards. A magnetar's reach is galactic. It doesn't need to swallow you. It just needs to sneeze in your direction, and we have no warning system. The physics of flaring offers no comfort. The magnetic field decay that powers a giant flare is a slow, inexorable process. Even if we had a precursor, our response options are minimal. You cannot deflect a gamma-ray beam. You cannot absorb it. You cannot negotiate with it. The civilization that receives them must cope as best it can. There is no shelter. Underground bunkers will not help. The gamma rays that ionize the atmosphere travel through rock and concrete and earth with no resistance. The energy is too high, the spectrum too hard. A bunker might protect you from the subsequent secondary effects: the electromagnetic pulse, the ionospheric disruption, the radiation-driven changes in the upper atmosphere. But the initial blast wave crosses the planet in milliseconds. Survival for those deep underground is possible. For the rest of the population standing in the open, experiencing the ionosphere's sudden brightening and the sky's sudden ringing, there is no protection. The most vulnerable moment comes in the hours and days after the flare, when the ozone depletion takes effect. Surface ultraviolet radiation rises. Phytoplankton in the ocean begin to die. The base of the marine food web collapses. The organisms that depend on it follow. Within weeks, the starvation begins. Within months, the cascade works its way up the food chain. Terrestrial crops, already stressed by the sudden UV surge, fail. The agricultural systems that feed billions of people cannot recover in the timescale of months or a year. The biological infrastructure that supports human civilization is not redundant. It is not hardened against this kind of shock. Magnetars do not hunt us. They do not aim or choose. They are not sentient. They are not malevolent. They are simply massive magnetic fields spiraling through the last moments of decay, discharging their energy according to physical laws that care nothing for biology. But that is what makes them dangerous. They do not care. The universe does not care. A magnetar speaks because the field has wound tight enough and the stress has built high enough that the crust breaks or the magnetosphere snaps. The direction the beam points is random. The distance it travels is irrelevant to the flare itself. The outcome depends only on geometry, on whether we happen to be in the way. That is the honest description of what occurred on December 27, 2004 at 21:30 Universal Time. A dead star 2/3 of the way across the galaxy unwound a spring that had been tightening for 10,000 years. It released more energy in 0.2 of a second than the Sun produces in 150,000 years. The beam swept across the galactic plane. We were standing in its path, and we survived because of distance. Not because we were warned, not because we were protected, not because we had done anything to deserve it. We survived because of an accident of distance, an accident of geometry, an accident of magnetar birth and drift and age and magnetic field decay happening to point away from us instead of toward us. The next magnetar will not care about luck. The next flare will not ask for permission. The next event could come from any direction, from a magnetar at any distance, carrying the signature of a dead star that decided at that moment that it had held its field long enough. And the galaxy is full of them, waiting, winding, ready to speak. But we will not hear them coming.